In this video, we will talk about the precise definition of a limit. So I want to motivate this with an example in which f of x is a piecewise function that equals the square root of x if x is not equal to 9, and it's negative 4 if x equals 9. So let's begin by drawing a picture of this function. So I'm going to draw some axes. So let's draw some axes, and when x equals 9, the output, or the y value, is negative 4. So it's negative 4. So there's one point on the graph here at 9, negative 4. For all other values of x, it looks like the square root of x graph. And the square root of x graph kind of starts here, and then it curves upwards like this. Curves upwards like this. And normally it would sort of keep on going like this, but I have to skip x equals 9. And when I skip it, I'll get a hole. And then it'll continue onwards like this. So if I had been able to plug x equals 9 into the square root function, the y value would have been square root of 9, which is 3. Okay, so this is the graph of y equals f of x. So by looking at this graph, we know, or we could figure out what the limit as x approaches 9 of f of x is. By looking at the graph, that limit is 3. As the x values get super close to 9, but not equal to 9, the y values get really close to 3. Which roughly means, based off of our definition of what a limit was, this roughly means, I'll put this in quotes, as x gets closer and closer, as x gets closer and closer to 9, f of x, and f of x represents the y values, f of x, or the y values, get closer and closer. F of x, or the y values, get closer and closer to 3. Okay, so I'm going to put this in a little bubble. So this was our definition of a limit. The issue with this is, mathematically, this is a vague definition. It's using very imprecise language, like gets closer and closer. So our goal for this section is that we now need a more precise, a more rigorous way to define limits. All right, so that's my ultimate goal. I'm going to sort of lead up to that by doing some examples. Okay, and initially these examples might look like they're completely unrelated to this larger question, but we'll tie it back in. Okay, so part A of the example says, what is the largest value of delta such that if 0 is less than the absolute value of x minus 9 is less than delta, then the absolute value of f of x minus 3 is less than 1. Okay, so this might look a little bit abstract here. We got these inequalities involving absolute values. But in the previous video, we talked about how we can break down an absolute value of something minus something as a distance. So let's use that idea. This first inequality chain is saying that the distance between x and 9 is strictly between 0 and delta. So I mentioned this in our overview video, but this symbol is the Greek letter delta. So it kind of looks like a D, but the tip is sort of curved. Okay, and we've also talked about what strictly between means in a previous video. That means that that distance cannot be exactly equal to 0, and it can't be exactly equal to delta. And I see that because these inequality symbols don't have an equal sign. All right, so doing the same thing for this other absolute value inequality. This is saying the distance between f of x, remember f of x is y, it represents my y values, between f of x and 3 is less than 1. All right, so let's draw a picture and then we'll break this down. So let's draw a picture. We've already drawn a picture of our function, so I'm just going to draw that graph one more time. So I'll draw some axes. I will draw some axes. And then when x equals 9, the actual point was down here at 9, -4. Okay, and then everywhere else it looked like that square root function graph. And it skipped the value of 9 here, so we had a hole. And then it continues onwards like this. And the y value of the hole was 3. Alright, so I'm shifting this picture over a little bit to give myself more room. But ultimately what I'm hoping is, I want to find some number delta, and we'll get to delta. But I want to find a number delta that will sort of guarantee the then part of the statement, that the distance between my y values and 3, the y value 3, is less than 1. Okay, so I see where 3 is on the y-axis. So let's go a distance of 1 up from 3, and a distance of 1 down from 3. And I'm going to call this vertical distance epsilon. So this is the Greek letter epsilon. Okay, and we'd mentioned this in the overview video. This is a Greek letter epsilon. So if I go a distance of 1 up, that means this y value is 4. If I go 1 down from 3, that means this y value is 2. So I want to stay between those two y values. So I'm going to draw a horizontal sort of dash line here through the y value 2, and then a horizontal dash line through the y value 4. And notice that these lines, they intersect the graph at some certain points. So they intersect it here, they intersect it here. Let me draw a little bit more of the graph here. Let's find the x values where they intersect. To do that, I need to figure out, well, when does the square root graph have a y value equal to 2? So when is the square root of x equal to 2? And I also want to figure out, well, when is the square root of x going to be equal to 4? So with both of these equations, I can solve them by squaring both sides. So the first equation would give me x equals 4 if I square both sides. The second equation, if I square both sides, would give me x equals 16. So x equals 4, that's going to be the y value here. It's not to scale. Okay, and then the second point at y value is going to be 16. All right, zooming out a bit, going back to what part A is really asking, I'm going to rephrase this. The question is, when it talks about this delta and the distance between x and 9 is allowed to be between 0 and delta, what that's really saying is how far from x equals 9, from a reference point of 9, can we go so that the y values are f of x, are in between these two horizontal lines I drew when y equals 2 and when y equals 4. So I'm going to make a little section here, and I'm going to call this the epsilon equals 1 window. So how far from x equals 9 can we go so that the y values are going to be in that epsilon equals 1 window? So in other words, what I mean by that is I need the y values to be within 1 of y equals 3. So as far down as 2 and as high up as 4. Okay, so that is our question. So to answer this, let's first figure out, when I start where x is 9, how far I can go to the left and how far I can go to the right before I would reach the edges of this epsilon equals 1 window. So if I start at 9, and I were to go all the way to this left edge of that epsilon equals 1 window, that distance is 5. If I were to start at 9 and go all the way to the right edge of this epsilon equals 1 window, from 16 to 9, that distance is 7. So I need to now know what is the biggest distance I could go from 9 in either direction that will guarantee that I stay within this epsilon equals 1 window. And it has to be in either direction. And it turns out that if I go a distance of 5 in this direction, that would guarantee in either direction, delta equals 5, that would guarantee that I stay within that epsilon equals 1 window. And if I go 5 to the right, I would end up at 14. If I go 5 to the left, I would end up at 4. But notice that I can't go a distance of 7, because I can go 7 to the right, but if I pick 7 for my delta, I need to also be able to go 7 to the left. And if I go 7 to the left, I'm way past 4. I would be all the way at x equals 2. And that's bad. I need to be able to go that distance that I pick in either direction to stay within this epsilon equals 1 window. So if we draw in that part of the graph now, so from this left edge, I'm going to just draw a line up. And from 14, from the right edge, I'll draw that part up. Let's look at the part of the graph, those y values that are in between these two sort of endpoints now. So if I look at this distance statement in terms of delta, it says the distance that between x and 9 is strictly between 0 and delta. And we've picked delta to be equal to 5. Because it's strictly between 0 and delta, it means I can't quite reach this endpoint, and I can't quite reach that endpoint. But I can be closer than that. I can be closer than that. I can be closer than that. And the distance also is not allowed to be equal to 0, again, because of the strictly between phrasing, which means I can't be right at this point where x is 9. So in fact, the actual point on the graph where x equals 9 was this one. And we've sort of forgotten about it a little bit. But that point is definitely outside of the epsilon equals 1 window. It just turns out that that doesn't matter because we don't care what's happening at x equals 9. This point doesn't matter since the condition that 0 is less than the absolute value of x minus 9 means that x cannot be equal to 9. So that's why we don't care about what's happening right at the point where x equals 9. So we're ready to state our answer. What was our largest value of delta? We had it a while ago, actually. We were just giving some more justification. Largest value of delta is equal to 5. All right, next I want to do part B of this example, which is almost identical. It's just we changed this number over here from a 1 to a 1/2. So we're making that distance smaller this time, that I can go in the y direction. So I want to begin by drawing a picture. I'll just set up the picture again, but then I want to give you some time to try this one on your own. Okay, so I'll draw some axes. I'll draw x equals 9. The y value at that point is -4. Okay, and then the rest of the graph is the square root graph. There's just a hole here where x is 9, and then it continues on upwards. This y value at the hole is 3. Alrighty, so from here, I want to give you an opportunity to try it. So pause the video for 3 minutes to try this question on your own. 4, 3, 2, 1. Pause the video and try this question on your own first. Alrighty, so hopefully you've done that. Hopefully you paused it for about 3 minutes to try it. So in this question, now the distance between f of x, my y values, and 3 needs to be less than 1/2. So this is my epsilon. Epsilon represents my vertical distance I can go. So this time I can go up a distance of 1/2. That would put me at 7/2. And I could go down a distance of 1/2. And then 3 minus 1/2 is 5/2. Let's make our epsilon window. Let's draw in some horizontal lines. Some horizontal lines. Okay. And let's draw in some shaded circles at those points. And I want to know what the boundaries of this epsilon window are. So I want to know what this x value is, and I want to know what that x value is. But let me label this window. This is now an epsilon equals 1/2 window. So to get those x values, I'm going to set my square root function. For one of them, I need the y value to be 5/2. For the other one, I need the y value to be 7/2. All right, so we can square both sides of this to get rid of the root, and that gives us x equals 25/4. Doing the same thing with this other equation, I get x equals, and then squaring the other side, 49 over 4. So let's label those. This point is at 25 over 4, that x coordinate. This x coordinate is at 49 over 4. Okay, so I need to know how far away are those from 9. Okay, so I need to know what this distance is, and I need to know what that distance is. So it'll help to get a common denominator with a 9 and those other fractional terms. If I multiply the 9, top and bottom by 4, I get 36 over 4. That's what 9 equals. So now for this distance, I got to do 49 over 4 minus 36 over 4. So that is 13 over 4. For this other distance, I got to do 36 over 4 minus 25 over 4. And that is 11 over 4. And then looking at those numbers, okay, I see that 13 over 4 is the bigger out of the two. And now I got to think about, well, what is the biggest distance, delta, I could go away from 9? So if I were to go that distance in either direction, it guarantees that I stay within this epsilon equals 1/2 window. So the biggest distance is, it turns out I will sort of run into this left end point of my epsilon window first. And that distance, delta, is 11 over 4. And I can even go 11 over 4 in this direction. And that'll guarantee I stay inside the window. If I go 11 over 4 in this direction, and I add 11 over 4 to 36 over 4 to 9, I'll get 47 over 4. It would be incorrect to say that delta, the biggest delta, is the 13 over 4 distance. Because if I pick delta to be 13 over 4, I need to be able to go 13 over 4 in either direction. But if I go 13 over 4 to the left, I'll go way past the edge of my epsilon window, and I don't want that. All right, so now if I draw this part of the graph, because of these inequality symbols, there's no equal sign. I can go up to this distance, but not add it, so open circles. And I shade in everything closer, shade in everything closer. And then because that distance from x to 9 cannot be equal to 0, I can't be at this point where x is 9 either. So we are just limiting ourselves to these red y values. So the largest possible delta in this picture is 11 over 4. And that's our answer. Okay, so we did these examples. How does this relate to the idea of a limit and giving a more precise definition? Well, the idea is, if we can do what we just did in part A and part B, in part A we did it for epsilon equals 1, in part B we did it for epsilon equals 1/2. If we can do this for every value of epsilon that's greater than 0, no matter how small, then the limit exists. Okay, so with this idea in mind, we are now ready to state a more precise definition of a limit. Okay, so this is called the Epsilon-Delta definition of a limit. So we are going to say that the limit as x approaches a of f of x equals L if for, so now I got to use this idea and just sort of translate it to more precise language. So if for every epsilon greater than 0, so now I need a mathematical way to express, we can do this. We can do what we did in the picture above. So if for every epsilon greater than 0, there is a number delta, greater than 0, that's going to be a distance, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L minus what I think the limit is, that needs to be less than epsilon. All right, so that is my definition. And I know right now this looks very technical. I'm going to end this video by doing a demonstration in Desmos to show you, well, what does this look like visually. In the next video, we will use this definition to actually prove that a limit of a function equals what it is. All right, so here we are in Desmos, and I want to do a short demo of this epsilon-delta stuff. Okay, so right now I have an epsilon value of 4 entered, That's why this graph is sort of going up 4 units above 3. That's why it goes up to 7 here. And then down 4 units below y equals 3. And that's why it goes down to -1. And right now, delta equals 0, and we'll play around with that a little bit. But I just want to show you, if I click on this limit thing, I can change what I want my a value to be, what x is approaching. So if I wanted it to be 8, I could. If I wanted it to be 9, which is what I have in my problem, I could. Okay, so let me hide this. And now let's play around with our epsilon values. So let me go to 1, because that's what we did in part A. And now I'm going to start to play around with my deltas. So what we found was the delta that worked was 5. So right now, this is what's happening if I pick a delta value of 7.7. Notice how far I'm going away from 9 and to the left and to the right. I'm going a distance of 7.7, and that's too far. I end up a little bit below the epsilon equals 1 window and a little bit above. Let's start to shrink that delta distance. And once I reach 5, just like we got, now that guarantees, even if I go a distance of 5 in either direction away from x equals 9, I am guaranteed that my y values are within this epsilon equals 1 window. Okay, so now let's shrink our epsilon. Let's do 0.5 like we did in part B. Okay, now my delta is too big. But the definition says, well, can I shrink it far enough so that I end up within the correct window? And yeah, I can. Once I make it small enough, I end up within that epsilon window still. So our definition says, well, if I can do this no matter how small I make epsilon, what if I make it 0.1? Let me zoom in a little bit more to the graph. Can I still shrink delta far enough to guarantee that I end up within the epsilon window? And yes, it turns out I can. And if I can do that, if I can continue to do this no matter how small I make epsilon, then the limit exists. This is how we're going to make that idea of closer and closer and closer more precise.